In this video, we're going to go over a fourth example of a bijective function, and we're going to make it interesting. We're going to define a function h that goes from the integers to the naturals and assigns n to, it is going to be a piecewise function, so it sends n to 2 times n if n is positive or equal to 0, and minus 2 times n plus 1 if n is negative. Now let's start with injectivity. We could have started with surjectivity, but whatever. So we need 2 elements in our domain, so n1 and n2, that are elements of the integers, set of integers, such that h maps both of them to the same object. So h of n1 is equal to h of n2. Now here we're dealing with a piecewise function, which means that we don't immediately know what h sends n1 and n2 to. But what we can do is separate it into 2 cases. We'll start with the case in red where n1 and n2 are positive or equal to 0. So now we know what h sends those 2 objects to. h of n1 is equal to 2 times n1. h of n2 is equal to 2 times n2, and they're both equal by virtue of this equality right here. And all that's left to do is multiply both sides by 1 over 2, and this will give us what we wanted. n1 is equal to n2. For our second case in green, we have negative integers. So if n1 and n2 are both negative, then h of n1 is equal to minus 2 times n1 plus 1, and h of n2 is minus 2 times n2 plus 1. They're, again, both equal by virtue of that same equality, and all that's left is some simple high school algebra. We multiply both sides by minus 1, we subtract both sides by 1, and then multiply both sides by 1 over 2, and this will give us, again, what we wanted. N1 is equal to n2. Now that's it. H, with this, H, we've proven that it is surjective, not surjective, injective. If you consider other cases, like n1 and n1 is positive or equal to 0 and n2 is negative, this will lead you to a contradiction. Okay, this is the symbol for contradiction, so you don't have to do this. Okay, don't do this. This is an unnecessary case to consider right here. But what about surjectivity? Okay, H is also surjective. So to prove this, we're going to need a natural number, so an element in our codomain, and we need to find a pre-image for m. The cases that I'm going to try to find or separate it to is when m is even and when it is odd, okay? Because when m is an even natural number, I'm going to try to find a positive or equal to 0 pre-image. And when it is odd, I'm going to try to find a negative pre-image. So that's how I'm trying to find my pre-images. So if m is an even number, so we can write it as 2 times n, where n is a natural number, then we can simply write m as h of n. Because a natural number is greater or equal to 0, we're using the condition in red for our function h, and so we can simply, h sends n to 2 times n. For our second case, we're going to have m to be an odd number, and you can write an odd number as 2 times n plus 1, but in this case it's going to be easier if we consider m to be equal to 2 times n minus 1. And in this case, we're going to need to omit 0, so where n is a non-zero natural number, we need to omit 0 because if we replace 0 in this equality, then we're going to have m is equal to minus 1, and it will no longer be a natural number. So we omit 0, and what I'm going to do is factor out a minus sign so that it looks a little bit more like this right here. This is my goal. M is equal to minus 2 times minus n plus 1. And this looks like h of minus n, right? And it is the case, okay? This is equal to h of minus n. We're going to be using the green condition because n is a positive natural number, so minus n is necessarily a negative natural number, a negative integer, I mean. So we'll be using the green condition to assign minus n, and we'll have this equality. So what we can do is conclude right here that h is surjective. We've exhausted all of the cases for our arbitrary element in the codomain. So h is surjective, it is injective, so it is bijective. Now take a moment to appreciate what we've proven here. We've established that there is a one-to-one correspondence between the set of integers and the set of natural numbers. So although the set of natural numbers is included in the set of integers, there is still a one-to-one correspondence between the set of integers and the set of natural numbers. If you take minus 2, minus 1, 0, 1, 2, etc., and you write the natural numbers in the column, so 0, 1, 2, 3, 4, etc., what you can do is assign 0 to itself. 1 will be assigned to 2, 2 will be assigned to 4, and for the negative numbers, minus 1 is going to be assigned to 1, and minus 2 will be assigned to 3. And if you use this rule, you're going to cover every element in both sets. That's pretty cool.